So I thought I would, well, thanks for the invitation. And I thought I would do it very informally to allow for lots of questions. So don't worry about putting your hand up, just ask in the middle, that's probably the best. I'll pause sometimes, but just ask questions. And I understand, so most people here are string theory background, is that true? How many people are familiar with like Lindblad equations and open quantum systems? Some, okay. And how many people are more like familiar with path integrals, that kind of way? Okay, so slightly more. So I can present either way, the path integral formalism or the master equation formalism. When we get there, I'll ask maybe. But I understand I probably will have to spend a bit of time on motivation. And if I can't motivate it, then there's no point presenting the formalism. So ask lots of questions about the motivation. And so let me give the motivation. The motivation is that gravity is not a force. It's different to the other matter field. So we know that, of course, gravity in quantum theory is inconsistent. And the usual way for the last, say, since the 1930s to try and resolve this consistency is the assumption that gravity should be quantized like the matter degrees of freedom. And I'm partial to that. I come from quantum information theory. I want to quantize everything. And so the question is, must we quantize it, the gravitational field? And so this will explore that approach, that question. And the conclusion is that there is a consistent, mathematically consistent dynamic. So for a lot of the history, people did not even think you could find a consistent set of dynamics which coupled classical systems and quantum systems. So we'll see that there is a consistent set of dynamics. I'll maybe. A little lower. So the general formalism I'll call classical quantum or CQ. Okay, so classical systems interacting with quantum systems. CQ. And what we find is that it's consistent. We find that pure states, pure quantum states, say pure, which is strange. We find that it's experimentally testable. And at least in the gravitational degrees of freedom, for the pure gravity theory, it's formally renormalizable. For the gravity theory, at least. So we don't need to talk about gravity. We could just talk about a quantum system interacting with a classical system. And I think I'll be giving a talk during the conference, and I think in there I will mostly focus on the renormalizability and the full theory. Here I just want to more talk about the motivation and the formalism. But we can also go off in other directions. Is there questions? Yeah? No, so I mean the pure gravity theory. So we just have the gravitational degrees of freedom. We don't know what happens when we add matter. I'm hoping to talk to the people here about that if anyone wants to chat. I'm around for the next few weeks. Does that answer the question? Yeah, that would immediately, we would know, like that would not be consistent with observation because the electromagnetic field is so strong that it would just, everything would just decohere instantly and the vacuum would blow up and all kinds of stuff would happen. So that would be bad. Okay, so I guess the word consistent means different things to different people. So let's define that. before we define it, let me motivate why, because I think your question is, if I can imagine what's behind your question, it's like, well, we have all these other forces, we could do this to anything. Why gravity? Yeah, so let me motivate that, and then we can discuss what we mean by consistent and why gravity. Other questions just about where I'm going so that we're on the same page and people know what CQ means and classical quantum and all that stuff. Yeah. Yes. Yes.
Saying all that can be made consistent, even though the viewing apparatus may be classical.
Yes, yes, indeed. And again, we discuss what we mean by consistent. So.
I know. So I was just asking your question.
Oh yeah, so in that, right, so let's discuss that when we get to the, I will discuss something called the decoherence. Let me put it even here, so we have some topics sitting here. The experimentally testable thing is something called the decoherence diffusion trade-off. In electromagnetism, we're going to see that renders the theory unstable. So it doesn't work for electromagnetism because of this reason. There's also the ultraviolet catastrophe in electromagnetism. I mean, there's a bunch of things that go wrong. We don't have as we were discussing at lunchtime, in gravity, the ultraviolet catastrophe is very mild. Things happen so slowly that you don't need to care. Whereas in electromagnetism, it would just lead to disaster. So electromagnetism leads to disaster partly through this. We will discuss this thing. And then as a foundations of quantum theory person, I'm intrigued by the fact that there's no measurement postulates. It's not needed. And what we tend to call collapse, yeah. Finn, did you have a, no, okay. Okay, so I will try and talk about these things and get you as far into the formalism as possible, but if I can't motivate it, then not much point. Okay, good, so the motivation is the following. So the motivation, and there's a, okay, so first let's talk about the motivating as a fundamental theory. And the reason is that gravity, I think if you come from string theory and high energy physics, you are treating it, you tend to treat it as just another field like every other field. If you come from a more relativistic background, which is maybe mine, we think of it as geometry. So gravity is not a matter field. It's the only, it's not even a force. It's geometry. So gravity is geometry. And it's the only one that we can write as geometry as a universal geometry. Okay, we can always, of course, write things in terms of connections, write any force in terms of connections, but it's the only force that we can write as a universal background geometry in which all the forces live. So I like to think of, we have this arena, which is curved space, and within that arena we might have the charged bosons, which go between charges, and gravity is this dynamical background which gives us our causal structure, and no other forces have that property. Okay, so it's the only one. And in some sense, it's not even a force. When I'm free falling, I'm just going through a geodesic, no forces are acting on me, so gravity is fundamentally different to the matter and forces.
particles which move into this.
Yes.
Then already this distinction becomes a little loose, right? Because you have a field and there's also a metric field. So the
Good.
basic postulate is some.
Good.
If you want to say that a lump of a field follows the geodesics.
There's two things there. Let's maybe, I'm not sure if I'm going to answer your question precisely, but let me try. So in a gauge theory, we have these gauge fields. So gravity is not a gauge theory. So gauge transformations act on internal degrees of freedom. They act on phi of x at the point x, okay? So we have a gauge field. The gauge field lives on the space-time point, and the gauge transformation acts on the internal degrees of freedom of the gauge field. Well, so the diffeomorphisms are moving the space-time points. It's actually acting on the space-time points themselves and moves them.
But they induce also a transformation in fields. Sorry, I was just saying, you could think of diffeomorphisms as inducing a transformation on the fields. So you would say G mu nu goes to G mu nu x plus D mu epsilon nu plus D nu epsilon nu, where epsilon nu is your
yeah,
small
there's some
parameter.
I guess I would say that in addition, and you will appreciate this, I think that if I have diffeomorphisms, there is no local degrees of freedom. So unlike a gauge theory, there is no meaning to, a degree of freedom at a point x. So that's the consequence of that, which I think is different to the gauge theory. So maybe that's one way to see the difference. But I agree with you. It's fuzzy. It's not like super obvious. These questions, they're subtle. Yeah. Yeah, there's topological. You mean topological theories?
I was just saying that there are gauge theories without local degrees of freedom.
Yeah, Chern-Simons. Yeah, I can have topological degrees of freedom which are not local. These are not topological. I mean, there are topological degrees of freedom, but
Topological.
yeah, but I mean, there's something different, right? And it's hard to get your finger on it. I think the maybe another way to get your finger on it is the Wheeler-DeWitt equation. So if I were to quantize diffeomorphisms, then what it tells me is that the super Hamiltonian annihilates the quantum state. And that tells me that at least in the bulk, where I'm implementing diffeomorphisms, nothing evolves. And so you have some ways of dealing with that, like relational degrees of freedom, or evolution is happening at the boundary, and we do it with respect to that clock time. But again, it's different. There's something going on that's very different from gauge fields. And there may be a way around this, but people have tried. So, like in the canonical quantization community, people looked at relational degrees of freedom. It was very hard because, clocks, you can have a physical clock and do everything. You think of evolution with respect to that physical clock, but, eventually that clock will run backwards, and you can have the boundary time and do everything with respect to the boundary time. That's very similar, but maybe there's no boundary that works for ADS-CFT. Does that work in general? So, there are these questions, and none of them, I don't think any of them are like absolutely definitive, but there's differences. Yeah.
Just to get a preview, this is really a redundancy in description, the Hamiltonian constraint as you wrote it. Of course, there's an integrated version of that, which is the Gauss law.
Yeah.
And what that tells you is that if you have a superposition of energy eigenstates in the matter sector, the metric gets put in a superposition of metric states. So are you going to say that that doesn't happen, right, in CQ?
Yeah, exactly. So one of the main things is we don't have this problem. This is a very quantum problem, right? This in some ways is saying, because if you know the energy exactly, then by the end, I mean, never say the energy time uncertainty principle, never say it. I'm not going to say it, but I'm going to say something almost close. If the energy is definite, then this thing doesn't evolve. And so classical physics doesn't have this problem. You can have well-defined energies, you can impose the constraints and still have evolution. So, you know, we don't have this problem. Now, one thing, we'll get to the fundamental theory. If you know, I think these issues, in my view, it's a bit unclear to me how different it is. And I guess my view is it's enough that I would try out to see if I could make this theory work. It's different enough that I don't think it's obvious we should be quantizing gravity. There's a question there. I would have, I think, originally been on the side of we should quantize it like we quantize everything else. I think the fact that it's renormalizable then makes me go a bit in that field, makes it feel more reasonable. And if you think of the history of quantum gravity, you know, people first tried perturbable quantum gravity, it wasn't renormalizable, so they gave up and then went to like string theory and loop quantum gravity, et cetera, which are UV finite. But this theory is renormalizable, so it's maybe some other route.
Let me just ask a preview question, which is, at least I think that the key feature of quantum gravity is the following, that if you take the key feature, I think, of quantum gravity is the following, and I think a lot of things follow from this, even though it's simple. You take a superposition of two energy eigenstates in the bulk. So you have an electron, and you put it in, you localize it a little bit. So you put superposition of, and then you go far away and use the metric. You measure the ADM Hamiltonian. Yeah. And you will find that the ADM Hamiltonian is in a superposition according to, if you use the relativity equation. Yes. And your answer is going to be that it will not be in a superposition. This is, in principle, an experiment we could do if we had technology. And you kind of measure the energy using a big, I don't know, some detector. And you just see how does the detector respond if you put the source in a superposition. And you'll say, you'll have a different answer to that than the standard one, which would be the detector would also go into a superposition.
I will have a different answer, and I will even say that we want to do this experiment. And I will speak about that next, maybe once. Yeah? Is there a hand? No. Any question? Good, yeah.
Yeah, would you say gravity is not a gauge theory even in 2+1 dimensions? I mean, there's a sense in which people...
In 2+1, I would say it's a topological theory, and yes, you can quantize it, but I don't think it tells us much about.
But it's still a gauge theory, right?
I mean, I think the main thing that kind of gets me in a tailspin is this, the one way to just think of gravity in its simplest way is that in different points in space, time is moving at a different rate, right? That's like 90% of gravity. It's just that component of the metric. So at different points in space, we have time moving at different speeds. And quantum mechanics is the theory where you have some, time, parameter time, and you describe the system in terms of that, and you have some slicings. And so the two just don't seem to fit from the beginning in a very fundamental way. And I think one has to really hit that head on. Now, even at the very beginning, and maybe I'll put this as more of the motivation, and that's to do with the causal, so this point is to do with the causal structure. So when we define fields in quantum field theory, we define it, we take these, it's phi of x doesn't, is going to commute with phi at x prime if these are space-like separated, if x and x prime are space-like. Even to make that statement, to define the quantum fields, we need to know if they're space-like, and if we don't, you've kind of someone's kicked the chair from under us, and we can't even say that. Even to define what we mean by the initial value problem, well, okay, what are we going to do? We're going to pick some initial surface, so t equals 0. That we need to know the metric in order to know what a space-like hypersurface is. So, okay, we can pick one without knowing what the metric is on it and do things perturbatively, but then if our theory is not background independent, that's not going to work. So even the initial value problem somehow, how do you pick a spatial, how to pick the spatial surface here at t equals 0 and even define things? Well, I mean, you know, the metric doesn't even commute with itself in a quantum theory, so I don't even know how you pick that. The different degree, the different components of the metric? Yeah. This is true. Yes. You think you can, that's enough to know if it's, you need to know how it's embedded. Do you not know how, do you want to know how it's embedded in the 3+1? Yeah. Yeah. I mean, you'll get in trouble. It's a bit like, I mean, this is not an operator which commutes with itself at different times. So, yeah.
You know, in the end, you just specify the initials data, right? I mean, you know, yeah, on a Cauchy slice, it commutes. Yeah, we kind of know how to deal. Yeah.
Well, so what people do is they do it perturbatively. Let's just pick one, and then we have the fields acting perturbatively on them. But then you need everything to be background independent, and we don't know, and you know, there's reasons to imagine it's not. So maybe that works.
In some cases, like in 2 dimensions or something, you can go beyond that, and you can really quantize it. And you can ensure that all your constraints are met. So it's right to then ultimately.
Are we talking about canonical quantization here? Are we talking about canonical quantization? No, I don't. I think so the question is this: can I pick a classical Cauchy surface, and then so I'm already taking space-time to be classical here, and then the idea is if everything is background independent, that choice of classical background doesn't matter, and that only happens if you know, we have the symmetry group of relativity. So if it's diffeomorphism invariant, that will happen if the constraints can be imposed, but that does not happen. I mean, we were so far away from being able to impose the constraints.
In 2 dimensions, you can do all of that.
In 2 plus, yes.
You can carry out the program.
Yes, in 2.
Other pieces, all I'm suggesting is it may not be a deep fundamental issue.
No.
It's carrying out.
Yeah, so in 2+1, of course, in 2+1 we don't have the problem because we have no local degrees of freedom. So that's true, but it doesn't tell us anything about higher dimension.
You really can do it.
Right.
Anyway.
Yeah, I'm not so. My statement is not that these are clearly conceptual things which mean we cannot quantize gravity. My statement is that these may be more than technical impediments. They may be conceptual and maybe telling us that we can't do it. Now, I'm not saying I don't know, and but I think it's a reasonable question to be asked. And I mean, I've been given 1 to 3,000 odds. I think I took a good bet because I think I think things are quite murky, and I think a lot of the reason that we're convinced that we must quantize gravity is historical. It comes from no-go theorems, which have since turned out to be not true, and it comes from people thinking that the semi-classical Einstein equation, where you put expectation values, that's the only thing you can do, which of course gives you superluminal signaling, all kinds of things, and is not what we'll be doing. So I think there was this conflation of classical gravity with the expectation value equation. There were the no-go theorems, and from a sociological point of view, people have not taken this position seriously. And I just want to take it seriously. I think all of you may be absolutely correct that it's the wrong approach. I have no idea.
I just want to comment on the fact that I don't think it's all for historical reasons. We have theories of quantum gravity. ADS-CFT are theories gives us many examples of quantum gravity theories where you could ask all of these questions in detail. Now, it's true that we don't know how to do that in our space-time, but I mean, these questions are all well posed, and there's a very well-defined research program that one can follow to answer those.
Yeah, and one that I follow and admire. I would be, so first of all, I would agree with you that yes, maybe it works if we have a boundary. And one of the key things is if you have a boundary, then you have a classical space-time, then you can have a time, then you can define your commutation. You can do everything because you have a classical space-time. So everything we do kind of hinges on having this classical space-time there. Like we always just use it. And the aim of quantum gravity is to kick that away. And it's not clear that we can kick that away. I'm a slightly less, I'm a bit more cautious when it comes to, say, ADS-CFT in the sense that I think, of course, you have a quantum theory on the boundary, which is you can define to be your quantum theory of gravity. I feel like the rules that people are doing are very much in a state of flux, and we do not know if you can consistently map that to a gravitational theory in the bulk. So, people still are arguing about whether it's dual to an ensemble or a single theory. We have new rules dealing with evaporating black holes. We have questions like state dependence and maybe that we need complexity arguments to get us around the Wheeler-DeWitt equation. So we have these quite radical things we're trying to still understand in ADS-CFT, and so I wouldn't go so far as to claim that we have a consistent theory in that case. We have a consistent theory on the boundary, but we don't know if we can map it into the bulk consistently.
I think you're right, that maybe the main issue has to do with the fact that people have not understood how to do synthesis. So that's, as you say, I would have thought about the same kind of communication.
Right. Yeah, so let's do it. I mentioned that the motivation is partly fundamental, and then there's also an effective theory, like, all we mostly care about are black holes in classical space-times and how they evaporate and what happens to the information we put in them. Or maybe we care about cosmology, where we have inflation and the vacuum fluctuations. We want to understand that. So we often want to have an effective theory. And then I guess I think as a toy theory, there are many issues in quantum gravity, like the constraints, for example. It's very difficult to solve the constraints in quantum gravity, but you can solve them more tractably in this theory. So, there are many situations in ADS-CFT which we might get stuck, and I think this also provides a toy theory which is more tractable, which we can use to understand some things like the Wheeler-DeWitt equation, boundary unitarity, things like that. Okay, so that's it for the motivation, and what I'll then do is talk about this, this decoherence versus diffusion trade-off, and this experiment, and why things go horribly wrong in electromagnetism. Questions about the motivation? Do you want to do like a little stretch, or? Okay. I'll use this board here, maybe. Okay, so this is the decoherence versus diffusion trade-off. And it's a bit like this thought experiment that Suvrat mentioned. So let's imagine we have a heavy molecule, and we put it in a superposition of being here and there. So it's either here or so we put it on the left or the right. So it's in a superposition of being on the left or the right. If it's a statistical mixture of being on the left and the right, that presents problems for, do people want to talk about semi-classical gravity, or can we just put that aside? That's when you replace the expectation value. So you have G mu nu equals 8 pi, and then you take the expectation value of T mu nu. Are people familiar with this? That's a problem. Don't do this at home, because if you have even a classical mixture, then that looks like two half particles, right, with half the mass, because we're taking the expectation value. So it's like two half masses here, and if you drop a test particle to go down the center, and the two half particles will be attracted to each other to where they would have been if we'd put them on the other place. So we don't use this. Yes, indeed. So it's consistent as long as the fluctuations are small in comparison to the mean.
But only in the limit where you don't have such a
Yeah.
you start doing such superposition, then you run the problem. Larger, what you mean is that everything is superposition fluctuations are very small.
Yeah. So if
If you have do big fluctuations like this, the wave function is part of the
You have to stay anyway with the
for instance, if you take a superposition of geometry, then you shouldn't be trying to satisfy this. Satisfy only geometry. Yeah, but that's not the same. You wouldn't take the expectation of PDD across all geometry and then write down some joint to satisfy.
yeah, we need this requirement. We
normally works you have a DE mu expectation and the metric response to that through this equation.
if the fluctuations are small. Yeah, like it's not so similar to Born-Oppenheimer, but you need that the fluctuations are small. And what we're of course interested in is the opposite regime here. So
Yeah, if you have contrived can just be a superposition of two states, right? You take a superposition of black hole here and a black hole there. You can say that's contrived, but it's a state in the theory, and that would already not satisfy this.
in quantum gravity, we care exactly about these. We have a, yeah.
No, if you
Heavy lump here and another heavy lump there.
no, I put the wave function in a superposition of here and there. Then the metric is not not given by that, right? It's not given by taking the average and then solving the Einstein equation. The metric is given by solving the Einstein equation each branch of the wave function. Otherwise, you'd run into this trouble, I think.
Yeah, I mean, even the classical mixture, you run into problems, and the reason is simple. When you're taking the expectation value of this equation, there are correlations between where the matter is and what the metric is. And when you take the expectation value, you destroy correlation. So this is why I'm giving this talk at a quantum information and quantum field theory and quantum gravity, is because in quantum information, we know all about correlations. That's what we do for a living, right? We know about entanglement. There could be entanglement between the matter degrees of freedom and the gravitational degrees of freedom. There could be classical correlation. And so we should never, and there is a correlation, right? When the particle is over here, the gravitational field is in a certain state. When the particle is over on the right, the gravitational field is in a different state. And when you take the expectation value, you throw away that correlation. And we know from quantum information theory that we should keep track of that correlation. We should write a density matrix or a master equation, right? We should write a density matrix which encodes the correlation between the matter degrees of freedom and the gravitational degrees of freedom. And that's the problem with the semi-classical Einstein equation. That is the main problem. We've thrown away the correlations, and we want to keep them by looking at the density matrix of the gravitational degrees of freedom and the matter degrees of freedom. Question?
Where it's a linear
Do you want to grab a?
the average value is in the center.
Yes.
The average value is half.
Okay, is
The
half.
average value is, you don't get half a star.
Yeah.
The average value is half at point -1 and half at point 1. But you really have a full star. It's not like the metric is responding to half this percent.
That's right. The expectation value of the stress
But I mean,
tension.
if I made a lump of the star highly concentrated on the left and another lump in the wave function on the right,
Yes.
and there's just no overlap between them, and I solve the equations,
Expectation value is still half.
the
No overlap.
okay, but I'll get the expectation value for the metric to be half, of the situation where it was on the left, or half of the situation where it was on the right. And I'd say there's a probability, because there's no interference between the two branches, I'd say there's probability half that the star was on the left and then the metric was this, and probability half that it was, that's fine. No one's going to complain with that.
But if you measure the star, you find it in the left, then the metric is not half. The metric you expect
No,
is
because,
full on the left. There's a full
okay, anyway, we should go, but you just said probability half star on the left and metric corresponding to star on the
That's right. So we would have, if you wrote it as a density matrix.
Right, and metric on that. And then you measure it's either this or that.
Yes. Yeah. Yeah. So in this, if we take a statistical mixture, like we flip a coin, half the time the planet's on the left and the gravitational field, half the time it's on the right. That is actually a problem. It's not a problem conceptually because we just say, oh, it's actually on the left. We put in that value and we don't actually, when we say take the expectation value, we don't mean take the expectation value. But there's a problem because we need to put words in that aren't in that equation. So you're putting in some additional thing into this equation by saying, I'm going to measure whether it's on the left or right, and then use this equation. If you have a superposition, you don't have that option of saying, I'm going to tell you whether it's on the left or the right, and then put in. So if it's even if it's in a statistical mixture, we still have this problem of two half planets, and the test particle going down the center, and the two half planets attracting each other. In the superposition case, it's even more clear because we don't have the luxury of, say, post-selecting or something like that.
Maybe what Sandip is saying is you have to consider now at least see the problem with back reaction and then you see.
Yeah.
If you just solve the first order integral, you get the right expectation value. But that expectation value is the metric. If you now try to consistently solve for the matter, it will give you a problem. Now you see the non-linearity.
Yeah.
Okay, we should talk more. I still think that there is no interference with math. Okay, go ahead, please.
45 minutes to the talk. Maybe also, so that was mostly about the motivation and what we don't know how to do.
Okay.
At some point, what we know how to do.
Okay.
No, it's much more interesting. Please go ahead.
Okay, so good.
Please go ahead.
Yeah. I mean, I think it's important I think I'm around, I'm happy to go through formalism. I think the general motivation is important as well. And I think conceptually it's important to understand, what it is we're doing. So let me, we're not going to use the semi-classical Einstein equation, but I want to give you a phenomena which has to happen, which you don't need the formalism for, but just through a thought experiment, which was the one that Suvrat mentioned. I have a particle which is in a superposition of being on the left or the right, and I want to ask what is the gravitational field that this heavy molecule produces when it's in superposition. And this, in some sense, was Feynman's argument about why, and all arguments subsequently about why we must quantize the gravitational field. And it's behind the experiments. And it produces some gravitational field. Now, if it was just on the left, it would produce one gravitational field, right? If the molecule was on the right, it would produce a gravitational field as if the molecule was on the right. And now I put it in superposition, and now what I'm going to do is I'm going to use a pendulum or a gravitational wave detector and try and see if I can measure the gravitational field to determine where the particle is. Is it on the left or the right? And I can measure, if the gravitational field is classical, let's imagine that, I can measure the gravitational field to arbitrary accuracy, right? There's no back reaction. There's nothing stopping me from measuring it everywhere. So I measure the gravitational field to arbitrary accuracy, and if the gravitational field is different when the molecule is on the left versus when it's on the right, then I can use that classical measurement of the gravitational field to determine whether the particle is on the left or right, and then it would collapse it instantly to being on the left or the right, and I would never see interference patterns, which we do. So something else must happen in order for this theory to be mathematically consistent. And the thing that happens is that the classical field has to be stochastic. So it has to be a statistical field theory. So we have the gravitational field has to be a statistical field theory which has stochastic fluctuations. And so now when you measure, which is what quantum field theory has, right? If I measure the vacuum, I can't use that to determine which slit a particle went through. Now, if I try and measure whether it's on the left, I measure the gravitational field, or I try and measure whether it's on the right, then the stochastic fluctuations in the gravitational field don't allow me to determine with absolute precision whether the particle is on the left or the right. They maybe give me some information about whether the particle is on the left or the right, but they don't give me enough. And so there's this whole region, say, in between, based on my conditioned on my measurement results, which allow the particle to remain in superposition. And so this is this decoherence versus diffusion trade-off. So the diffusion, the diffusion is what we call the stochastic nature of the gravitational field. If you can have long coherence times, it means there must be a lot of stochasticity in the gravitational field. And so the idea from an experimental point of view is to go out and measure push coherence bounds to be longer and longer. And the longer the coherence time is, the more we expect there to be stochastic fluctuations in the gravitational field. We can do a precision measurement of the gravitational field. Gravity is very weak. And so there could be a lot of stochasticity before we would notice it. And so that's the trade-off. This as a coupling constant we call D0, this we call D2. And so there's some trade-off between the two of them. Something like D0, D2 has to be larger than that. So we have this trade-off, which we can go and look for experimentally. So that's the experimental proposal on how we would go and confirm the quantum nature of space-time. If we can put an upper bound on stochastic fluctuations and a big enough lower bound on coherence times, then we could rule this theory out. And it's, I think, constrained enough that you could probably rule all classical. So you could effectively determine the quantum nature of space-time by squeezing the theory out in both directions. So that's the experimental proposal. And you can kind of see that that's maybe the insight as to how this thing is able to be mathematically consistent.
Hello.
Yeah.
Sir, am I audible? I actually had a question regarding this stochasticity. So up to what orders should one look at, and up to what moments one should look at the stochasticity that the theory can predict?
Right.
Is it just the mean or the variance, or higher moments are also retrievable from the theory?
Yeah, so I guess what you're trying to measure is it's the Newtonian potential. So you're looking at something like trying to measure this thing at x and phi at x prime. So this is the covariance matrix of the acceleration. So it predicts the stochasticity and acceleration. And so this 2-point function is what you want to measure. And usually what you do is so this is divergent, but that's the same with all other kinds of similar quantities in quantum field theory. So what you want to do is you want to smear this over some test mass.
Okay, so it's more or less the variance, something related to mean and variance, and not the higher moments that
That's right, yeah, the variance is what matters, yeah.
And if I were to induce quantum fluctuations to that, will I retrieve some higher moments, or will it be only reducible to the second moments of the theory?
Sorry, the question was, are the higher moments reducible to the second moments? Was that the question?
If I have theory, this theory, CQ theory, then will the classical moments be restricted only to mean and variance? And if I were to consider quantum corrections, will they be higher order moments induced to the stochasticity, or everything will be on the scale of mean and variance of 2-point functions?
Sorry, the speaker system is, I'm having a little bit of trouble hearing. I think you're talking about if there's a Wick's theorem, like if the first and second moments are enough to determine all the other moments, is that?
No, just an extension to that. If I were to see only the classical theory, will there be only first and second moments? Or if I were to consider quantum theory as well to that, will there be higher order moments induced to this one?
I think you're asking about like comparing the quantum theory to what it would predict with the classical theory. Is that right?
Yes.
In the quantum, so I should say, in the quantum theory, I don't see a reason why you need. So what is different in the classical quantum theory is that you have this trade-off. So you can go and do coherence measurements, and that puts a bound on that. If you have a long coherence time, you need a much larger stochastic fluctuation in the gravitational field. That does not exist in the quantum theory. So we don't expect you to see these fluctuations in the quantum case. They're there in the classical case. That said, there are claims, like I think Catherine Zurich, for example, there are claims that holography produces such fluctuations, but I'm not able to verify that. So there are claims.
Why I'm asking this question is with respect to the RMTs, where I can see higher order moments even up to the order n, arbitrary order n, at least for the quantum chaotic case. So will that be reproducible if I were to consider this, or is it just a mean field of that, what we are considering here?
Okay, so I'm having trouble hearing, but maybe we can discuss after, and I'll be here for a couple of weeks, so I would enjoy discussing that. Okay. So are there any questions about this trade-off in the experiment to detect it? I should say there's another set of experiments by Boza et al. And Marletto and Vedral, where you look for gravitationally induced entanglement, which can only be created if you have a quantum theory of gravity, so that could falsify this theory. And so there are these two experiments coming online, which for me is very exciting because, okay, we can debate all we want about Wheeler-DeWitt versus ADS-CFT versus whatever, but at the end of the day, this is an experimental question, and this does seem answerable. So we will, it might be like I think the estimates are like something like 150 million, maybe 10, 15 years. Maybe when LISA comes online, that will give us very good bounds for the stochastic fluctuations. So there's a lot of hope in kind of these experiments that we can decide the question.
Yes. Sorry for interrupting. Can I ask a question? Hello? So what would be the explicit form of the energy momentum tensor T mu nu corresponding to a mass that is in position superposition?
Sorry, what would T mu nu look like?
For the mass that is in superposition at x equal to L and x equal to R.
Yeah, so the point is that if you have a density matrix, then you just have this, you know, we never use this at all. We just write a master equation or a path integral, and then you have a density matrix which has both your gravitational degrees of freedom and your matter degrees of freedom. And so you never run into the problem of the inconsistency or anything like that. You don't write this down, and you would never write such an equation down if you had a stochastic theory. You wouldn't.
But okay, my point is that if you write T0, so the 0, 0 component of T mu nu, it will be a linear combination of mass densities at L and R. But I feel there will be cross terms when you try to calculate Tij, the spatial components. So could one say that this can be attributed to the, this can be attributed to the quantum nature of gravity, because on the right hand side you have T mu nu without the expectation value taken. So component wise, you solve the Einstein's equation, you get metric corresponding to T00, T01. Can we say that the right hand side will lead to or induce a quantumness to the left hand side?
I don't see that. I guess I don't think we can use this equation. So I mean, it's true that there's an operator that we can write down, which is a classical quantum operator, which has both operations on the quantum field and also gives you a value on phase space. So I can measure that operator, but but I need to measure it on the density matrix. So I think in that case you don't see this mixing occurring. But maybe that's for online discussion. Maybe that's best offline.
Okay, thanks.
And if people are away and are online, drop me an email and we can have a Skype. I'm happy to do that.
So if I could just intervene, just to answer, we have about 35 minutes and this talk will have a hard cutoff. We'll have the Chandrasekhar. So maybe if you do tell us a little bit about the formalism and what equation we should write down.
Yes.
That would be your.
One small thing, sorry.
Yeah.
And I want to promise
Okay, no, it's fine.
I mean, if I understand right, so if you had a classical field interacting with quantum matter, that would cause the matter wave function to decohere.
Yes.
But then if the classical field itself is stochastic, you can mask the effects of that decoherence. happens, right? Compared to a quantum system. Well, even if it's not precisely correct, my question was, when you construct a theory like this, you have various parameters.
Yes.
For example, how stochastic you make the classical field and so on. And do you just adjust those by hand or at will? Or, I mean, so you could always push the boundary in a sense where experiment is, where your, what's the...
Yeah,
Anyway,
okay, good. So
there
that's
seems to be some freedom in
yeah, so there's some freedom. So we have there's two coupling constants, D0 and D2. What we find is that two things happen when we saturate the trade-off. When we saturate the trade-off, two things happen. One is the quantum state stays pure the whole time, conditioned on the classical trajectory. And the other thing is that's when we can prove that the dynamics is completely positive trace preserving. So then you just have one new coupling constant, and it's a dimensionless coupling constant, and it runs. So we are introducing one new dimensionless coupling constant into the theory. This point about the pure state staying pure, I'll maybe give a picture. I should say I can maybe put a slide of some similar talks online, because there are, so for example, the first consistent CQ dynamics, there's some examples that were found by Tadashi and Blanchard and Jadek in the 90s. There's various references that are important, which I've kind of glossed over, but I can put that I'll put that in the slide deck. So what happens is, let's say we have the Bloch sphere. So we could imagine, for example, that we start off, say, let's start off here on the surface of the Bloch sphere. So a pure state, we can start off in the plus state, right? So a superposition of being left and right. And then what we will find if we saturate the decoherence trade-off, decoherence diffusion trade-off, is that the quantum state stays pure. And so what happens is that you either are going to you're either going to go along the surface of the sphere and land in the right state, or you'll go and land, let's see, in the left state. Sorry, I don't know if you can see that. But initially, because of the trade-off, we don't really know whether you're going to end up being in the left or the right. And so that's why you can have superpositions. And what's strange is that when you saturate the trade-off, this quantum state stays pure the whole time and is moving on the surface of the Bloch sphere, just in a zigzaggy path. And the path that I'm drawing is correlated with some classical degree of freedom, which might kind of do something similar. So this could be, say, pi, or let's call it P, the momentum, if you have a P and a Q. So this would be like a spin and a P and a Q. Or a particle in superposition. So that's what kind of the phenomenology of what is going to happen here. And so when I do the formalism, let's maybe think of the simplest system, which is a qubit, right? A qubit, so a spin two-level system, and then a free particle. So we have phase space. So we have Q and P, and then at each point in phase space, we have this Hilbert space. So it's like we have a fiber over this symplectic manifold of phase space. We have this Hilbert space here. And so we can think of it as we specify, to tell you where the system is, we specify P and Q, and then we have a density matrix for the spin. So I guess I'm starting into the formalism now, how it is we think about a classical quantum system. So you can think of a phase space density. So it has some probability distribution over being at a point in phase space. And then given that it's at a particular point in phase space, it has a density matrix. So we can think of this as a conditional density matrix. Given that we live at a particular point in phase space, we have a different density matrix. So that's the formalism. That's how we describe states. So we can also describe them. So we can describe them as a point in phase space like this, Q minus Q0. So if they're at the point at, say, at t equals 0, that they're at point Q0 and P0, and then given that, then we would describe them in terms of a quantum state psi, and that's kind of an initial state. That's how we would describe the initial state. And then you can, of course, have probability distributions over this, but you can never have entanglement, right? So entanglement we can only create between two quantum systems. You cannot have entanglement between a classical system and a quantum system. So one of the hallmarks of this, any classical quantum description is that you have you cannot have entanglement between the classical degrees of freedom and the quantum degrees of freedom. Question about how we describe the states? Yeah. So we will, let's call this, let me call the density matrix, so this is just an initial state. I'll write it as a density matrix. So let's call this the classical quantum state, so CQ, and I'll put a little hat because it's an operator. And so the CQ state is, we can write it in terms of over Q and P. So for example, it is a density over Q and P, and then say a state in the Hilbert space. Yeah, Q and P are phase space, and then psi lives in the Hilbert space. So we're living in both. Because they're classical. So we have a classical degree of freedom, and so classically we can, it's not. So if this was an effective theory, then we might think about a coherent state, and we're approximating the coherent state by its average Q and P. So there's a whole interest in what is so I call this the classical quantum limit. We have two quantum systems. We want to take the classical limit of one of them while keeping the interaction there and keeping the other system quantum. That's weirdly not much studied, but that's. Go ahead, question? Yeah. So let's do a Stern-Gerlach. That's the easiest thing we can do, right?
Maybe this is where you're getting to, but this is what you said is not true, but there are these old papers by Gizon and Polchinski that say whenever you do this and you turn on interactions, you run either into problems of superluminality or interference between branches of the wave function. And you're saying that's not going to happen, right?
Sorry, when do you
This is at the time of Weinberg's nonlinear quantum mechanics and papers by Gizon and Polchinski, which looked at descriptions of this kind, where you had phase space coupled to,
No, they looked at this kind.
Exactly.
And good, so that's another thing we're going to require. So we don't want to run into these horrible superluminal problems. But more to the point, we want to respect, so what does this thing have to satisfy? It has to be positive because it gives us a probability, right? So this has to be positive. Because we still want it to be a density matrix. It gives us probabilities. We're not going to mess with the state space. We're just messing with the dynamics. So it has to be positive, and it has to be norm preserving. So norm preserving. And so the norm here is that, so the norm here, so the norm is 1, and we integrate out dq dp, and then we take the trace of rho hat dq. Okay, so if I just call this trace preserving but we're integrating over phase space. So that's the norm. All the probabilities have to sum to 1. And so the dynamics has to be CPTP. So that's a condition. That's the consistency. Dynamics must be CPTP. Yeah. Yeah. Yes, but I guess what that might give you is something very strange, and it might not last for long. So, for example, in order to have the observables representing Q and P and having them commute, then you need to have them like live on different Hilbert spaces, right? So you'd have like a system which tells you what Q is, a separate system which tells you what P is, and that's very artificial. And I suspect that would break down very quickly. So I call this an embedding. You can embed your classical quantum system into a fully quantum system, but it would not probably last for very long. At some point, this would break down. Yeah, the dynamics, after some time, it would no longer be a good approximation. I think there does exist some dynamics which will preserve it, but I don't know if you would be able to preserve like the commutation relations between Q and P, for example, the classical Poisson bracket, sorry, with Q and P. That might be hard to do. And as soon as you have so you might be able to do it for a linear Hamiltonian because things work easily for a linear Hamiltonian, but for any one with a nonlinearity, I think it would break down. I think that's an interesting question. Like this is a notion of embeddability. Can you embed it in a fully quantum system? Because of course, one of the arguments you might make is, well, okay, fine, you can write this thing, but I maybe can find a embedding where it's a fully quantum description. I don't believe you can, but that's a possibility. Questions?
So is there a linear response theory for the quantum system that is coupled to the classical system?
I think so. So you're up on something different, but let's just say that the dynamics has to be linear in the density matrix, so you don't have these problems that Polchinski and Jazan and people found with Weinberg's theory. So it needs to be linear, but you're talking about like linear response theory in terms of like some thermodynamics weak coupling. Is this what you mean?
Yeah, so if one has a linear response theory, then it would be more amenable towards experiments, like you know the susceptibility, like how it responds to the perturbations.
Yeah.
And then by calculating that, you can compare that with the theory. Like,
yeah, I think one should be able to do something like that. I mean, I guess people are now become interested in this just from a like condensed matter system or thermodynamic system, because in thermodynamics we often deal with situations where we want to treat, say, the walls of our container and the heat bath. We want to treat it classically, but the system itself we want to treat quantumly. So there is this interest in such condensed matter thermodynamic systems. There you often might not care about complete positivity because you just think it's I don't know, sometimes in chemistry, but they don't care about positivity. But here we do, so that imposes some additional constraints. But I think, yes, I think you should be able, a lot of the machinery that is of interest in, say, condensed matter or statistical field theory should work here.
Also, would the notion of temperature emerges from this formalism?
Yeah, so if we get there, I'll say that the purely classical dynamics looks like a Fokker-Planck equation, and the purely quantum dynamics looks like an open quantum system.
Okay.
So there's people here interested in kind of open quantum field theory. I'd be interested in talking to people about that because, you know, the purely quantum dynamic. So maybe, how are we for time? We're almost ending. 15 minutes. So maybe I would just say briefly that if I want to look at the So you know, remember in quantum mechanics we have the Schrödinger equation or the Heisenberg equation. So di rho di t is equal to minus I h bar rho, or let's call this sigma. That's quantum mechanics. In classical mechanics, we have similar, right? We have the Liouville equation, I wrote IT equals Poisson brackets, H rho. So the equations formally look very similar, right? And then in quantum mechanics, we can ask for the most general equation. So now the question is, can we combine these in a sensible way such that it's completely positive trace preserving? And if you're a quantum information theorist, that's your bread and butter. You know, we did Krauss maps, we did all these things, and now we get to do it again. And so we can run this machinery and ask, what is the most general dynamics which, you know, reduces to this form and is completely positive trace preserving? And we've found the most general dynamics, and there's a continuous version and a hopping version. And so you end up with terms that look like the Lindblad equation in the quantum case. So in quantum mechanics, you get this Lindblad equation, which let's say has this d0 over 2 and might have some, I'm going to pick Lindblad operators. So that's an example. So this is called the Lindblad equation, and it's for open quantum systems.
I'm confused with this equation where the units go. The D0, I believe, is a diffusion length. It's sort of decoherence time.
Yeah, exactly.
And so it's time. So, but it's inverse time on the left-hand side. And then there's an H bar somewhere.
Yes.
Where's the H bar?
H bar is 1, C is 1, everything is 1.
But T is also, because
Yeah.
T and 1 over T does not have the same unit.
Sorry? So this would have an H bar, so this would have a 1 over T here, this is a 1 over T, and then it'll depend what your Lindblad operators are here, what D0 is, but you can pick it to have the right unit. So in gravity, it's like, it has units of 1 over G Newton squared in natural units. Yeah.
This evolution has some Krauss operator decomposition.
Yes. Yes.
But now you're going to tell us how to combine it with the one.
Okay.
That's what it's
Yeah, that's right. And so the one below the most general form is something called the Fokker-Planck equation, which looks like, and we're going to have some other operators here. So this is called a D2. You have a diffusion. And let's write this as, also you can write it as a double Poisson bracket. And we will pick I will just pick, Q here, for example. But this could be any function of Q. So let's just pick some function here, rho. So this is there's a double Poisson bracket here. So it's very similar in form to the Lindblad equation. This is called the Fokker-Planck equation. And it gives you diffusion, it's Brownian motion. It's just Brownian motion. You get some diffusion, you can have some friction. And this is actually, so just like the Lindblad equation is the most general CPTP infinitesimal equation, the Fokker-Planck equation in continuous phase space is the most general, completely positive, norm-preserving equation. And now we want to couple them. And so we're going to have this and this together. And the thing that it will be new is something called the Alexandrov bracket, which looks like 1/2. And we're going to have some Hamiltonian H rho plus 1/2. So this is the back reaction. And there's an operator ordering issue here, ambiguity. And so we're going to use that. So in actual fact, the CQ state, sorry, this is now being a bit quickly here. So we're going to write the CQ state as just like this. So rho hat is going to be a phase space density Q and P, and then conditioned on that, we'll have a density matrix QP like this. Okay, and so what we're going to do is, this is only acting on the one part, but we'll stick, the whole equation will include all terms. Sorry. Yeah. So, And now we're going to put the CQ state in here. So this acts on both of them, right? So this has, so this acts on both terms. And I'll give you, it'll be easy to have a example, I think. That's right, so this will give you a matrix out. D rho by dt is also a matrix, right? Sorry, I should rewrite it everywhere. So I'm going to do it like this. So I'm going to put here, we're going to do this. I'm going to change this. So everything now has got the same thing. And then plus, we're going to add these terms here. So we have the purely classical evolution. So this is all CQ now. So we're going to add in everything together. So we have the purely quantum evolution. It's like quantum field theory in curved space-time, some decoherence. So this is like quantum evolution, but this can depend on phase space. Then you have the purely classical evolution.
This is why I was harping on the H bars.
Yes.
It seems to me that where's I mean, you have the same units. You bracket up there as 1 over H bar.
This will have a 1 over H bar.
It does not.
No, but it works out because you have a Q and P, right? It's diQ, diP. So Q and P have the same units as H bar in. Yeah, it's the standard way. That's right. So indeed. So here the ordering matters, and because this is an operator. And so here we do the Homer-Simpson method. We take both orderings and divide by 2. Yeah, yeah. Well, the rest don't need it because so let's write it with, let me give an example that'll be the best. So the example we're going to have is we can have H, the purely classical one. Let's call this purely classical. This could be P squared over 2m. Okay, so just free particle. And then we're going to have an interaction. So let's add to that. Sorry, this is really cramped. An H interaction. This is an operator, and let's take Stern-Gerlach. So we're going to take Q, and we're going to take the spin. Okay. Okay. Let's not worry about the Hamiltonian for the particle. So now, so we don't, and so, although we have it here, so H, we'll take the full H to be, as an operator, to be H classical plus H. That's right, yes, yeah. So you have the pure classical evolution, which is it's going in a straight line, and then you have this one, and I can write what that will look like. So let me write it out. We have di rho, CQ, di T. The important part is we'll have, let me write out this part here, okay? So you'll have 1/2, right? So then di rho di Q, so that just gives you a sigma. So you have sigma here, right? Di rho di P plus 1/2, and then sigma on the other side, like that. So this is the back reaction. So you can think what it says. If the spin is up, it moves the momentum in one direction, right? Because this is just a linear velocity, just a force, a back reaction. If the spin is down, it goes in the other direction, right? By this thing. So if the spin is down, then if the spin is up, then both of these will just push it this way. If the spin is down, both of these will push it that way. But if it has for the off diagonal elements, it'll push them in different directions, right? Because let's imagine that we start off rho in the plus state, rho at 0 is equal to, say, the plus state, superposition, then the top left density element will go up, the top right will go down, and then the off-diagonal elements will get confused, right? One will get pushed in the one direction, one will get pushed in the other. And that might look like it's going to break CPTP, but these additional terms will ensure it doesn't. So what is this term? This term is just decoherence. So this just looks like D2 sigma. Sorry? Sorry, this is the D0, sorry. Yeah, D0 will go rho sigma. So this acts to suppress the off-diagonal element, right? Because this is 0 on diagonal elements, but causes exponential decay on off-diagonal elements. It's just... You can, but there's the trade-off. So you need to, then if D0 goes to 0, then D2 has to be large. And this part is, this just looks like di rho squared, di p squared. So this is pure diffusion and causes, so we have that the Stern-Gerlach, the particle will move to, will gain in momentum. If it's spin up, will lose in momentum. If spin down, I may have got the sign right. But this will cause huge amount of diffusion in the momentum. And so it'll do something like this. But eventually I'll be able to figure out which path it went to. So this causes diffusion in the momentum so that you can't tell if it's spin up or spin down until you wait long enough. And meanwhile, this is causing decoherence, so that when you can finally figure out that it was spin up, it is decohered by that point into being spin up. And that's what allows, when you saturate this trade-off, you find that what happens is that the particle starts out in being the plus state and then slowly moves to being, say, in the left state or the right state. Okay, all the while staying pure. So that's the dynamics. It's just to remind you, it's got this strange back reaction term, which has an operator ordering ambiguity. It has the decoherence term, and it has the diffusion, and they conspire in just the right way to keep the state pure.
If the classical Hamiltonian is not quadratic, if the classical Hamiltonian is not quadratic, this doesn't have any restrictions on.
Yeah, you can do it for any. I can give you any Hamiltonian. So an example like this was found in like the 90s. Examples like this. So now we can do it with any Hamiltonian. So we have the most general form, and then what we were able to do is look at for GR and do a path integral formulation. So.
The nice classical limit, for instance, you can check that if you put the quantum system in some coherent state, you get back what you'd expect would be the classical equations of motion, or
yeah,
that can also be shown.
So in this system, it's fairly easy. So you were asking about, like, say, field theory and what one does, and there's more subtleties. So you need to somehow think about coherent states, like how you take the we call it the classical quantum limit. How you take the classical quantum limit is tricky, because you want to kind of turn off these things while taking the classical limit, because you might find that there's a classical limit but with a huge amount of diffusion, for example. So there's different ways of taking the limit. So the classical limit could be GR but with stochastic noise, and that's actually what we find.
Explain the question that Sandip asked, and I was also asking at the beginning, which is you now do a two-slit experiment, and then you do this Feynman thought experiment, which is you shine a beam of light to try and see which slit the electron went through, and you couple them in this way. So, as I couple the field and the light, the particle in this way, what is the prediction? What do you see? You see an interference pattern or not?
So we get that you should see an interference pattern, but I will have two caveats. There is a trade-off. So eventually, the hope is that you could rule it out. You could rule it. I don't want to say hope that you can rule it out, but you can either rule it out or in. That requires really precision tests of gravity and also, so people are very impressed. Oh, light hardly does anything. I mean, the difference between the stress energy tensor of light is. Oh, you're talking about the electromagnetic field. Yeah, that would instantly, you would instantly decohere. You wouldn't be able to get lights in superposition. Yeah, you would see that you need a huge stochasticity because the back reaction is enormous. I mean, electromagnetism is so much stronger than gravity. So this can hold for gravity because gravity is so weak, but for something else, it wouldn't. Plus you have the ultraviolet catastrophe. No, here you can do it. So I think from a formal point of view, you can put, I think you can put every electromagnetism. I think it would just, so it's an experimental question. We don't see we see things in superposition, so it has to be.
I understand, but what prediction would it make? You know, the thought experiment is you shine a beam of light.
Yes.
You start with light very long.
Yes.
And then it doesn't, you see the interference pattern.
Yes, you wouldn't see an interference pattern. You would see two things. You would see you would not see an interference pattern, and the vacuum would just heat up like mad. Like you would just, it would be creating all this stuff, and you wouldn't be able to be alive. You would need such a high stochasticity. It'd have to be so stochastic that you would, see all kinds of things happening that we don't see.
Where one description is you have a classical phase space for the electromagnetic field, which is coupled in this way to the electron, to the charged particle.
Yes.
And the other is where you do the field theory, where you've quantized everything together.
Yes.
And these two things are just completely orthogonal. Is there some way they look, is there some parameter that you can adjust so that one would go into the other, or you're saying there's just different dynamics? I write down the Lagrangian of electromagnetism coupled to a charged field, and then I can quantize it this way, where I quantize the charged field but not the electromagnetic field. Or I can quantize it the standard way, which is I quantize everything together.
Yes.
And it would be nice to understand how that dynamics
so
differs. I mean, forget about the experimental consistency.
Indeed. Yeah, so this is like, what is the parameter space of a quantum to classical quantum theory look like? So what is the classical quantum limit look like? What's the parameter space? And that's actually very important, even from this point of view of these experiments. If you want to propose an experiment, well, we live in the classical world, so you're proposing an experiment in which we think we are measuring these things, and so you need to understand that limit. And what we find is that you get a different parameter space in that case, because Q and P, there has to be diffusion in both Q and P, whereas if it's a fully fundamental theory, then only one of them needs to diffuse. So it's just a different parameter space. But we don't understand that very well, and we haven't done it for gravity. So that's something that needs to happen if you're going to, go out and do these experiments, because you want to say, this is what we see not from the effective theory, but from the fundamental theory. Yeah, this one, yeah. Oh, sorry, that's just a Poisson bracket that went awry.
That's really the same term as what you had above.
Yeah, well, because of the operator ordering ambiguity, so I divide it into. Oh, yeah, I guess I'm treating them separately. I could put them together. This is the purely classical one, and this is the interaction. But indeed, I could put them together because it wouldn't make any difference. So here is the H classical, that's pure classical. Here is the interaction. I could include them together. That's right. I do this, and I have this. So it's F. I haven't told you yet, but it's related to these Lindblad operators. So in this case, it would just be Q. In this case, it would just be Q. So here, where was the A? Okay, so H is Q and sigma, so L is sigma and Q is F.
General algorithm, if I give you a general H, how do I figure out what's L and what's F?
You effectively write out this thing in terms of a set of Lindblad operators. So these are, it's a bit more complicated. There is a general algorithm for
Takes
doing
you from any edge to an L. So you give me an edge, you'll produce an L and an F.
Yeah.
And this is the dynamics.
That's right. And there's even more general than that, because I don't need to give you a Hamiltonian theory. There are other theories which fit into this description, which are not even generated by a Hamiltonian, but the more interesting ones are probably the ones that are generated by Hamilton.
You just explain that a little bit. How, in this case, you even separated out the p-squared terms. So somehow that didn't play a role in L and F, which is a little strange. Because there's p squared by twice m
Well,
plus
that
q
wouldn't really
sigma
matter
hat,
because
and
there's no, this is just a pure,
Because it has an
if I
identity.
include it in the Lindblad thing, it would just commute and give 0. So
I see. But not in F, right? It would do something for F.
Well, the F, I mean, you know, basically it's the coupling terms which you have a coupling term, and if the coupling term, if it doesn't have a Q, then it will not appear here, and if it doesn't have an F, it won't appear here. So, and this is not the most general form actually. This is continuous in phase space. There are other. I mean, I'm happy to go into this a bit more detail offline if there are people that are interested. I'm happy to arrange an hour. We can Blackboard. I can give it in more detail, but it's maybe a bit technical for people that were not convinced by the motivation.
You have that equation d0 times whatever was d2 had to be greater than equal to some number when you started. And if it were equality, then the behavior could not be distinguished from a quantum system, say for this.
Oh, no. So with equality, what we get is that the pure state stays pure.
Pure.
And I guess that's a special interest because even just foundationally, like say you want to study the black hole information problem. So what this tells you is that, okay, there is a toy theory where we treat gravity classically, where the quantum state should stay pure. So if information is being destroyed, then we should see it in this toy model, right? So it gives you a toy model, for example, to study the black hole information problem, because normally under evolution, pure states would stay pure, even though there's some breakdown in predictability. So you have a breakdown in predictability because the phase space causes like a measurement to happen.
Just without going to something as complicated as information loss.
Okay, sorry.
Let's say there's a hypothetical, it doesn't have to be electromagnetism, but some classical field or its quantum version, and we are trying to decide how to tell them apart. What precisely, are there situations where the dynamics, even though diffusive, etc., classical with a classical field, could not be told apart for the quantum part of the system from its quantum evolution? That is to say, in your example, we have the spin, which I'm thinking of as the quantum degree of freedom for the moment, and P and Q as surrogate for the classical. Now the spin responds to the interactions with the classical dynamics, and it traces out a path, which is when it's trace preserving, it's like a pure state, right? And so I thought in that case, you can't tell it apart from a quantum system in a suitable background, in a suitable background field. Is that zeroth order understanding correct? Or?
Yeah, sorry, I'm not entirely sure. It's just jet lag a little bit, but maybe I can say things which I think are answering your questions and which I think are true. Clearly, when we do measure, this is of interest to people who, I think this is where your question is going, are doing measurements, right? Like we are experimenters. We think we can write an effective theory for our measuring apparatus. And so it should, as an effective description, describe measurements if we believe in the many worlds interpretation. So there, yes, there's a parameter space where it should give you some effective description, which is around weak measurements and things like that. Now, if I then go, so that's a certain parameter space of the theory, which we don't understand very well. We've just, we wrote one paper about it. It's very confusing still. But then you can imagine that I say, okay, I don't want it just to be an effective theory. I want to know, is my measurement device fundamentally classical? And we don't believe that. And if you try that, you should get something which is inconsistent with what we observe. And I think you would, because you're trying to write down a Q and a P for your measuring apparatus, which it doesn't have. So you could do it in a kind of approximate way where you think of coherent states and you can say, okay, I have a measuring apparatus, and when I say that it has a definite Q and a P, what I mean is that it's in a coherent state around that Q and P, and then I can write a master equation for that degree of freedom. So you can do it like that. Is that answering the question? Yeah, maybe later. Yeah. Yeah. Yes. Yeah. Well, so the theory actually doesn't have decoherence in the sense that, as I said, conditioned on the gravitational field, the quantum state is pure. It only has decoherence if you trace out the gravitational field, then it looks like it's decoherent. So it's like a fake decoherence. It looks, which is what happens in a fully quantum description, right? In a fully quantum description, it's decoheres if I trace out my environment, but conditioned on the environment, my system is in a pure state. And likewise here, my system is in a pure state if I condition on the environment. If I throw away the gravitational field, it decoheres. So the gravitationally induced decoherence, which people like Roger Penrose and Joshi have talked about, happens here, but in a very different way. It's not a genuine decoherence. The quantum state is pure. Sorry, I'm going off into that tangent again, and maybe that's not what your question was. Okay. Yeah, okay.
Sorry, am I audible?
Go ahead, quick, one last question, and then we'll break for coffee.
Yeah, just like you said that as a whole system, CQ system, there is no decoherence. In that case, if I were to see the stochasticity of individual system, say classical system and quantum system, then we know that for classical systems, the stochasticity goes as 1 by f, while for quantum system, it goes like 1 by f square in the quantum chaotic case. So if there is no decoherence, then how do we match these things? Because there will be no loss of information, so the power spectra should match.
I'm having trouble hearing the question, and so feel free to email me. But I think what you're asking is, usually when we look at noise, they go like 1/m. In a harmonic oscillator, if I add noise, there's a certain spectral density that we can measure. This one has a different form, so that's also maybe why we can measure it, because it doesn't. For example, it's mass independent in the case of acceleration gravity measurements, which the usual, usually the fluctuations go like 1 over the mass. So the spectral density is different in this theory.
Thank you, sir.
Okay, so we'll come back exactly at 4 o'clock for the first Chandrasekhar lecture. So thank you, everyone. Thank you, Jonathan. Yeah.